Okay, so good morning, everyone. So remember, last time we were talking about LU factorization. Okay, so remember LU factorization. The motivation is, you try to solve a linear system. Well, you try to solve many linear system. Okay, with the different right hand side. Okay, but with the same matrix A. And what is the most effective way for you to do that? And so that is the motivation for the LU factorization. Okay. And then we define what is a lower triangular matrix. Okay, unit lower triangular matrix. And then we define what is the we define what is the upper triangular matrix. Okay, what is the upper triangular matrix?
So I can't buy the
then
you can't get insurance States, but you can use
say that
to access your
a matrix
to buy the things you need
when it has a LU factorization. If you can write A is a product of a unit lower triangular matrix. Someone is in mute. Okay, sorry about that. It's okay now, yeah. Okay, so now, so remember, we say that a matrix A can be written as unit lower triangular matrix times upper triangular matrix U. Then we call this a LU factorization of the matrix A. Okay, and we say that if you have a LU factorization, then you can solve a linear system AX equal B by two steps. First, you solve Ly equal B by forward elimination, and then you solve Ux equal Y by back substitution. Okay, so if you attended the online lab yesterday, then you then you know that how it is used in solving the linear system, but you will see that if you do the lab tomorrow or on Friday. And then you have seen the LU factorization. Actually, you've been doing it since first year algebra. Okay, so since first year algebra, what you did when solving a linear system is you did the Gaussian elimination. And when you doing Gaussian elimination, unconsciously you compute the LU factorization, okay, without knowing it. So this is the algorithm. So the algorithm, essentially what you are doing on a piece of paper can be written as a few lines of MATLAB or Python or C language or whatever computer language. Okay, and the L is the factors when you apply the row operation. And then I mentioned that, okay, so how we compute the LU factorization of this matrix. So we did it on paper. And if you look back at the video, you see that you do the row operation and then you get the upper triangular matrix, and then you collect the entries for the matrix L from looking back at the row operation factors. Okay, so then now, so we also discussed when you have a LU factorization. So, there's a theorem say that if you check on the principal submatrix and all of them are non-singular, it means that determinant are non-zero, then you have a LU factorization. And so this is the theorem, yeah. And then we did an example. We saw that, well, in some case you couldn't do the row operation because there's a zero in the wrong place, and you did it by swapping the rows. And swapping the rows, there is a name for that. It's called pivoting. So pivot elements are non-zero. So you interchange the rows or you swap the rows, And then this technique is actually equivalent to, you know, multiplying a permutation matrix by the original matrix. So remember, permutation matrix is just the identity matrix, and you swap the rows or you swap the columns. Okay, so then you get a permutation matrix. And so in effect, you know, there's always a way to swap the rows so that you got the swap matrix. Okay, the permuted matrix can be factorized into a product of L and U. Okay, and now instead of solving AX equal B, then you solve PAX equal PB. Okay, because you multiply P on the left and P on the right here. So you have to solve PAX equal PB. And then, you know, you replace PA here by LU. Okay, and LUX equal PB. Then you solve LY equal PB, and then you solve UX equal Y. Okay. So we also try some examples for that. So this one is when you swap row 1 and row 3, then you apply the row operation and you get a upper triangular matrix and lower triangular matrix, and now it's equal the swap matrix. Okay. And then in MATLAB, okay, so this one is relevant to assignment 1. If you start working on assignment 1. Okay, so remember the LU factorization can be carried out in MATLAB by the LU command. Okay, but you have to give 3 outputs, the lower triangular, the upper triangular, and the permutation matrix. So if you forgot the P, then the answer is not correct. Okay, so in this case, P is a permutation matrix that swap the first and the last row. Okay, so if you forgot, so in this case, if you forgot to give P, right, then you see the matrix L is not lower triangular. So it's not unit lower triangular. Okay, even U is upper triangular. So be very careful when you use the LU command. Okay, so you have to understand what is going on. So far so good, right? And then we discuss another example why you need to swap the rows as well. So this case is a very simple matrix, just a 2 by 2 matrix. But you know, you have a mu is a very small number here, and then 1, 1, 1. So all of them are very small number. And you see that in this case, you can work out the exact solution. Okay, and then the exact solution is given by this formula. Okay, and the condition number in the infinity norm can be computed, so it's around 4. So the matrix is very, very, very well conditioned. However, okay, now if you look at the LU factorization, okay, so the matrix L look like this. So 1, 0, 1 over mu and 1, and then the upper triangular matrix just mu 1, 0, 1 minus 1 over mu. So remember, mu is very small. Okay, so then 1 over mu is a very big number. And see what happened if I use MATLAB to run this, and what do I see? So now let me share my MATLAB. Okay, so you see, like I say that mu is very small numbers. What happened if I said mu is 10 to the minus 15? Okay, and then I define the matrix A. Yeah, so remember the matrix A is 1, 1, mu 1. Yeah, so if you look at the slide, and then, so actually, this is the second case. When we swap it, we have to uncomment this. Yeah, so this is the first case when I okay, so when I haven't swapped the rows. Yeah, so now you run it. And you see the relative errors is 0.07. Okay, so relative zero is about 7%. Yeah, and now what happened if I swap? So what happened if I swap the rows of the matrix A? So remember, now I swap. So this one is the original matrix, yeah. And then if I swap, then I run it again. So the relative error is equal to 0. So you see that if I swap the rows, yeah, the first and the second rows, then the relative error is reduced from 7% to 0. Okay. So you see there's a difference, yeah. And now, I mean, you can read it a bit more details in the lecture notes, but now let me focus on what is going on here. So we go back to the slide, and so you see that we saw that if you swap the rows, yeah, so if you leave it like this, mu1 and 1 1, then the relative error is big, right? But when you swap the rows, row 1 and row 2, relative error is equal to 0. And then the reason is, you know, if you change the rows, yeah, so the condition number are unchanged, okay, but the matrix L and the matrix U have changed, okay. And now you see, before you have a matrix L and a matrix U like this, so it has 1 0, 1 over mu and 1, and 1 over mu is very small, so this can be very big, right? But when you swap the rows, then now the matrix L is 1 0 and mu is a very small number, and U as well, so you have 1 1 and 0 1 minus mu. And you know, I mean, it related by this theorem. So you see now what happened is, so in this theorem in 1961, so suppose you have a matrix L and the matrix U, right? But then when you store in the floating point arithmetic, then you don't have exact L and exact U, but you have like L star and U star, okay? So then L star multiplied by U star is a perturbation of the matrix A, yeah? So you see now you don't have a original A anymore, but you have A plus some errors. And these errors, the delta A, can be controlled by this inequality, okay? So now rho n is not a big number, but the norm, infinity norm of A, well, depends on A, right? But in our case, this number is very small, right? It's about 4. But now you have a condition number of L star and U star, okay? So depends, yeah, so depends. In one case, it could be big, and in other case, it could be small, right? So when mu is small like this, then the infinity norm of L can be very small. But in this case, when you have 1 and 1 over mu, okay, and mu is like 10 to the minus 15, then this one could be very big. Okay, so that is what is going on. So then in our case, so this one is another consequence. Okay, so when you try to solve a linear system by the LU factorization, then you can have what is going on here. So this is a consequence of the previous theorem. And if this one are very big, then the errors could be very big, and that is what happened in our case. So now you can read a bit more in the lecture notes, but in it explained here. So in this case, you know, I mean, when you don't swap the rows, this quantity Okay, it could be very big number. For mu is a very small number. So that is what's going on. And then so partial pivoting. So partial pivoting is like you just swap the rows and you make sure that the pivot elements is always larger. And when you you check only in the absolute values of all the entries, you know, because there's many ways to swap the rows. Okay, so one way to make it unique is you can choose what elements has the largest in magnitude in absolute values, and you make it to be the pivot elements, and they call it partial pivoting. And MATLAB use this in the LU function. And so this is example how MATLAB is doing this LU factorization, and you know, I mean, you can go through it and in the lecture notes or in the slide. So again, it's just a Gaussian elimination, and you know, to save the memory, you store on the coefficient here. Yeah, the green one are actually just the coefficient of the matrix L. Okay, and then after you got to the final step, then you know the matrix L are just the blue part, okay, and you make everything equal 0. Sorry, you meant the diagonal is 1 and the upper diagonal just equals 0. Then you got the matrix L, okay, and the matrix U just this you know, upper triangular what you have left in the row reduced echelon form. And whenever you swap the rows, then you store that into a vectors, okay? So then you can give the permutation matrix, okay? So this one is just a simple example showing that how, you know, you compute LU factorization. Okay, so now remember last time we saw that I showed you this script already, right? So I can show you again. So why bother to study LU factorization? Well, because LU factorization make it faster when you try to solve many linear system, right? So remember we saw this one already, yeah? So one way is you solve a linear system by LU factorization. And another way is you try to solve it by direct Gaussian elimination. And by LU factorization, you will see that it's always faster, right? We saw it. And now we need to explain why is that. Okay, so now we introduce the, you know, operation count. You count how many floating operation, and then you can compare the two algorithms. So for example, if I take A and B are two floating point numbers, okay, I add them or I multiply them, okay, then you know, it is we call it one flop. One flop is just a shorthand for floating point operation, okay. And you see, you add by a negative number, like you divide, or you divide is you multiply by 1 over b, right? So you add in or multiply is enough. Yeah. And then, for example, suppose you have two vectors and you want to compute the inner product. Okay. Then we say that this one is about 2n flops. So why is that? Well, because, you know, I mean, you take x1 multiplied by y1, so 1 multiplication, right? And then you take x2 multiplied by y2, so 2 multiplication, right? So totally n multiplication, right? And then after that, you add all of them. So you got like n minus 1 addition. So totally is 2n minus 1 floating point operation. Okay. And then because, you know, we say that, okay, for very big n, then we don't care about the minus 1 here. So roughly about 2n. to n flops. Okay, so when we counted the flops, then we got somehow we counted the computational cost of an algorithm. So now suppose, you know, like I claim that if I try to compute L, the matrix L and the matrix U in the LU factorization, then it's about 2n cubed over 3 flops. So why is that? So why is that? So I claim that, you know, I mean, if I try to compute the matrix L, then it will take about 2n cubed over 3 flops. So maybe let me draw a diagram. So you see my whiteboard, right? So suppose I have a matrix A like this. Okay, so you see my whiteboard. Okay, so suppose I have a matrix A like this. So A11, A12 up to A1n, right? And then A21, A22 up to A2n. And dot, 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 then AN1, dot, 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 ANN. Okay, then I want to compute the LU factorization of this matrix. So essentially what I'm doing is I'm just applying the Gaussian elimination. Yeah, so I'm going to convert this into A11, A12, dot, 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 A1n.
We
right?
can't see what you're writing.
And then
sorry.
0 all the way down here. Yeah. And here I have some new entries, A22 tilde, A2n tilde, and so on, you know. So then I got AN2 tilde, ANN tilde. So some real numbers. So how do I get those A22? So A22 tilde is the, you know, A22 minus some k, some, can you hear? Sorry, so what you want to say?
We can't see what you're writing down. It's just blank for us.
Nothing show up. Cannot see anything. Sorry about that. So how do I? Okay, so now let me share again. So do you see anything now? So it's there now, right? Okay. So everything is okay, yeah? Okay, so you see now, suppose you have a matrix A, right? Then I want to compute the LU factorization. So what I'm doing is I'm going to apply the LU factorization. Sorry, what I'm doing is I just apply the row operation to get the row echelon form, right? So what I'm doing is I just apply the row operation from this step to this step. So I make all of these entries as 0. So you saw this before, right? And so this new entries is A22 tilde is A22, the original one, right? Minus some, you know, some constant. Maybe I call it K2, right? A11, sorry, A12, right? So you have to take this and you minus the some constant of multiply with these entries, yeah. And so K2, so K2 here is just A21, right, divided by A11, yeah, and then so on. So you can do the same for a 3 2 dot 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 a n 2 equal, you know, a n 2 minus k 2 a n 2, right? But now what I want to tell you is we are not interested in the values, yeah, but we're interested in how many operation you have used. Okay, so you need n minus 1 division, right, to compute the factors. So you need n minus 1 division to compute, you know, k2, right? Because every, well, actually every coefficient you have maybe this one, not k2 but kn, yeah. So you need n minus 1 division, right, to compute the elimination factors. So k2, k3 up to kn, yeah, because you got a k2 up to kn. And then now you need how many multiplication and how many subtraction. Well, so totally how many entries you have in this submatrix? So you have n minus 1 square entries in this submatrix, right? In the submatrix, right? And each of them, so you need like each of the entries, you need 1 subtraction and 1 multiplication. So you need like n minus 1 square subtraction and n minus 1 square multiplication, right? I mean, I'm just counting the flops here. The flops, you know, division, you need 1 flop, multiplication 1 flop, addition 1 flop, subtraction 1 flop, right? So then totally, right? So totally you have so for the first submatrix, right? Then you need like n minus 1 plus 2 n minus 1 square, right? Flops for the first submatrix, yeah. But then remember, you have to do it again and again, right? So until you got an upper triangular matrix, yeah. So you have to repeat this step. So you have to repeat this step again and again. So then what I want to say is, so the total, so this one is for only for 1 step, yeah. So for on the step, then what you need is you have n minus 1, right? And then the next submatrix will be of the form n minus 2, right? Plus 2n minus 2 square, right? And then the next one will be n minus 3 plus 2n minus 3 square, and so on until you have 1, you know, 1 plus 2 in the very end, right? So in the end, what you have is just the sum, yeah. So you have the sum. So you have the sum of I, and I run from 1 to n minus 1, right? Plus 2 sum of I square, and I run from 1 to n minus 1 square. Oh, sorry, n minus 1. Okay. And you see there's a formula for this sum, right? So if you look it up, there's a formula for this, and this one is just n times n minus 1 over 2, and this one is just 2 Okay, so this one I just use a formula. So there's a formula when you sum up on the square from 1 to n minus 1. Yeah. So you got n over cube over 3 minus n square over 2 plus n over 6. Okay, so believe me, you can prove that formula. Okay, so you agree now? So then totally you will see that this one, if you forget about the n square and n cube, sorry, you forget about n square and n, then this roughly about 2n cube over 3 flops. Yeah. So does that make sense? Okay, so now we believe it. Yeah, so I should let you believe it. So that is, we claim that how computing the L and the U roughly about 2n cube over 3 flops, okay, by counting the number of addition and subtraction and multiplication. And then you see now you use a big O notation. So remember 2/3 is just a constant, right? So roughly, you know, it's a big O of n cube. Yeah. And then when you try to solve Ly equal B and Ux equal Y, then roughly it's about 2n square flops. Okay, so this one, I wrote it down in the lecture notes already, so please read them. So I wrote the step for the LU factorization in the lecture notes as well, so please read them. So by counting the number of flops, you can show that when you solve the lower triangular system or upper triangular system, then it takes about only about n square flops. Okay. So now if you go back to the MATLAB here, so we try to explain that, you see, so this one, so suppose you have n is like 10 million linear system, right? And then if you solve it, okay, so now I didn't mention that when you try to solve the Gaussian elimination directly, then it will take about n cube flops. Okay, so then because you multiply, you do it again and again, so it means that the total cost will be, you know, capital N, the number of linear system multiplied by n cube, right? And now what happens if you use LU factorization? So if you use LU factorization, then okay, initially you have to compute the matrix L and the matrix U, so it will take about n cube flops. Okay, but then once you have it, you can reuse it, right? You can reuse it again and again. So you reuse it again and again. So then in each step here, solving the upper triangular or lower triangular, take only about n square, right? So the total cost here will be n square or n cube for the initial LU factorization. And then after that, you repeat this one n times, but each of them is about 2n square. Okay. And you can see that for very big n, for the very big capital N, then this number, okay, will be bigger than this one. Yeah. Because here, you know, you take n and you multiply n cube, but here you take n, you multiply only n square. Okay, so this somehow show you that if you use LU factorization, it will be faster when you try to solve, you know, many linear system with the same matrix. So another one, so there is another example. So this one is another program, you know, like, okay, so I'm going to run this. Okay, if you look at the assignment, actually it's very similar. Okay, so if you set a matrix A like this, so A is identity matrix, yeah, plus some random matrix of size n by n multiplied by half, and then you compute the LU factorization. Yeah. But what happened here is the size of the matrix is changing. Yeah, n is changing. So n come from this. Okay. So n equation is actually 500 multiplied by 1 to 10. Yeah. So you can see that n is 500, and then 1,000 and 1,500, then 2,000 and so on. Yeah. Then I compute the CPU time for, this one is just, again, if you saw the lab yesterday, so this one is just you compute the time taken to compute the LU factorization. Okay, so TLUK is just the time taken for computing the LU factorization. And then, okay, so this one is a mysterious formula here. So what does it mean here? So now, so what I want to do is, well, let me run it first and I explain what it's doing here, yeah? So you see, this is the program that in the slide. And now let me run it. So you see that the time, sorry. So the time is measured in seconds. So n is 500, 1,000, 1,500, and so on. Okay. And so what is exponent? Okay. So now look at the exponent. So exponent is like 2, 1.5, and then 3, and then 2.8. So then, okay. So now what is exponent? So now, let me explain. Okay, then you have to tell me whether you see the whiteboard or not. You see my whiteboard or not? Yeah. So let me clear this. Okay, so can you see it now? So now suppose I have n here, right? And then I have time Tn here. Okay, so then I have like this one is like some n to some power alpha. So can you see that? Yeah. So then, so suppose I have another one, say, so this one is n1, and so this one Tn1 and n1 alpha. And then I have n2, then I have Tn2, then I have n2 alpha, right? So then, so if I say that Tn1 is a constant time n1 alpha, Tn2 is a constant time n2 alpha, right? Then, I mean, I just take the ratio, then I got Tn1 over Tn2 equal n1 over n2 to the alpha, okay? And then I take a logarithm, so any logarithm is okay. So just take, natural log or, so again, okay, so in MATLAB, if you write log, it's a natural log, okay? So if you want log base 10, then you have to write log 10. So if I take logarithm like this, so here can be any base, yeah? Then the power coming down. Okay. And so you can say that, okay, so alpha will be the ratio between logarithm of Tn1 over Tn2 divided by logarithm of n1 over n2. Okay. And so this one is the way to find out what is the power alpha by just the program, So then that is exactly here. So if you go back to the slide, you will see that. So you see logarithm of time is tk over tk minus 1 over, so this one is just the nk over nk minus 1. So p actually is the power. So it gives you the power, right, of the time. So in terms of n. Okay, so this one, so it depends on your computer. So in this case, you know, I mean, the exponent is about 2.6 something, but every time you run could be a different, because, you know, I mean, your computer can have many processes running at the same time. So theoretically we should get 3, but we never get exactly 3, so we get something close. Okay, so now we stop the LU factorization here, and I want to introduce another factorization. We call it Cholesky factorization. So Cholesky factorization is, you know, when you have a symmetric and positive definite matrix. So what does it mean by a symmetric matrix? So symmetric matrix, it's just like when you reflect over that diagonal, they are the same. Okay, and in other words, if you take a transpose of the matrix, then you don't change the matrix. Okay, so that is another way to say it. And a matrix is positive definite if you take, you know, this quantity, you take any vector x, right? And you take x transpose multiply a multiply x, then it's a positive. Okay, so except when you have a 0 vector x. And if you expand this, yeah, then this one can be written as this double sum. So xi, aij, xj, and greater than 0. So this one equals 0 only when you have a 0 vectors. Okay. So give me an example of a positive definite matrix, a very simple 2 by 2 positive definite matrix. Yes, identity, right? I mean, if identity, then this one just x square, and then you know, I mean, x square is always greater than 0, so it's very good. So identity is positive definite matrix. And you see now something a bit more complicated. So this one is, you know, you can multiply this one out, and you know, this one you multiply this one out like this, and you complete the square. Okay, it looks complicated, but actually some manipulation, you can complete the square, and this one becomes the square, I mean x1 square plus another square here, and then another square here, then another square. So this one, because the sum of the squares should always greater than 0, except that when it's a 0 vectors, then they will become 0. So then this matrix is a positive definite matrix. Okay. And so how do we tell whether a matrix is positive definite or not? Okay, so suppose you have a symmetric matrix. So in this section, we just consider a symmetric matrix only. Then you can check whether the matrix symmetric, positive definite or not by checking the determinant. Okay, so determinant of all the principal matrix of order K. So essentially you have to check on the sub matrix, right, of order 1, order 2 up to order n. And then if all the determinant are positive, then the matrix positive definite. And you see, like suppose the matrix again in the previous example, you know, so if you look at the determinant, right, so A1 is just number 2, so then it's positive, and A2, then, you know, you got 2, 1, 1, 2, so determinant is just equal 3, so positive. And determinant A3, you can compute it by a formula or by MATLAB, and it's equal 4, so positive as well. So therefore, it's a positive definite matrix. Or actually, you can use the eigenvalues. So if all the eigenvalues are positive, then, you know, the matrix is positive definite. Okay, so I assume that's a symmetric matrix. So this one can be proved as well in linear algebra. So we can skip it. So now, okay, so now come to the main part. So Cholesky factorization. So now if you have a matrix, A is symmetric, okay, and positive definite, yeah, then it has a Cholesky factorization. So Cholesky is the man who first come up with the idea, okay. So, and the Cholesky factorization is A is written as R transpose R. So what is R? So R is the upper triangular matrix, okay, and all the diagonal entries of the matrix R is positive, okay. So now let me show you how to prove this, okay. So at least one way is very simple to prove. So this is a theorem. At least one way I can show you how to prove it. The other way you have to read it in the lecture notes. So let me share the whiteboard again. So I assume that you can see it. So now we have a matrix A, right? Equal R transpose R. Okay, so we call it Cholesky factorization. And we say that this one, if and only if A is symmetric, and positive definite. Okay, so at least I can show you this way. I can show you this direction. So now how do I show that A is symmetric? Well, so I just consider A transpose, yeah. So A transpose is R transpose R and the whole thing transpose, right? And you know, I mean, remember in linear algebra, when you transpose a product, then the transpose of the second one come first. So R transpose and then R transpose transpose, yeah. And then this one R transpose transpose just equal R, so you got R transpose R, yeah. And see, this one is just the original matrix A. So you got A transpose equal A. So therefore, by definition, A is symmetric. Okay. And then now how do I prove it's positive definite? Well, by that definition, so I take a vector X, right? And then I take transpose, I multiply by A, and I multiply by X, okay? And now instead of writing A, I write R transpose R. And then I still have X transpose here, then X here, right? Okay. And now remember that this one is just Rx, everything transpose. Okay, so remember there's some identity here. So A, B, so two matrix. When you transpose, it become B transpose, A transpose. Okay, so this is a identity I use, right? And another identity is now if you have Y transpose Y, yeah, then this one is just, you know, you have Y1, Y2 up to YN here, and then Y1 up to YN here. So this one is just Y1 square plus Y2 square plus up to YN square, which is just the two norm of the vector Y square, right? So I'm going to use this identity, right? And this one for Y is Rx, so then I got this one is Rx square, the two norm. And you see, there's a question. What is R again? Okay, so R is just an upper triangular matrix. So R is an upper triangular matrix. Okay, upper triangular matrix. And on the diagonal entries are positive. Okay, so this is the theorem. So, and we call it a Cholesky factorization. So Cholesky is the man, I mean the first man who proposed it. So Cholesky is moving. Okay, so now Cholesky anyway, I don't want to move the whiteboard, but you know, you can see that when you write matrix A like product of R transpose R is upper triangular matrix on the diagonal entries of R positive, then we call it a Cholesky factorization. Okay, so now go back to this proof. Yeah, so X transpose AX can be written as RX, the 2 norm square. So definitely this one is greater or equal 0, right? Because when you have square, right? Yeah. For all X, for all vector X. Okay, so now we have to check when Rx equals 0. So Rx equals 0, okay? Then it will imply that X will equal 0. Why is that? Why is that? Because, so remember on the diagonal entries of R are positive, right? So it means that R is a non-singular matrix. So when you solve a non-singular linear system, Rx equals 0, then you just have a 0 solution. Okay, so essentially now we show that Rx equals 0 only when X equals 0. So this one showing that. So now we show that X transpose AX is greater or equal 0 for all X. And maybe, you know, actually you can say that it is, sorry, so for all X, yeah, in Rn, and it equals 0 only for X equals 0. So this shows that A is a positive definite matrix. Okay, so at least we show that this is the case. Okay, so I think that I have this one in the lecture note as well. So if you have a look, and yeah, so it in the lecture note. So if you look at the lecture note, it's there. Okay. And now, so this one is example of a matrix. You know, like before we had that matrix, and when you compute the Cholesky factorization, then you have upper triangular matrix like this. Okay. And in MATLAB, there is a function CHOL will produce a Cholesky factorization of the matrix A. So the number of flops to compute the matrix R is about n cubed over 3. So half of the cost of the LU factorization. So it means that, you know, in this special case, when you have a symmetric positive definite matrix, when you use a Cholesky factorization, then, you know, it takes only half the time of the LU factorization. Okay, so then you can solve the linear system AX equal B by solving, first you solve R transpose Y equal B, then you solve Rx equal Y. So that AX equal R transpose Rx, right? And so remember Rx here equal Y, yeah? So Rx equal Y, and RTY equal B. So X is a solution of Ix equal B. So similar to solving by LU factorization, but it will be faster, right? So in this case, it will be half the time if you use LU factorization. So how about stability? So stability is given that it will depends on the condition number in the two norm of the matrix A, okay, and times the epsilon. So epsilon is a machine for epsilon. So we are not going to details, but essentially the stability still depends on the condition number, okay. So that is everything about linear system, and next week we are going to study interpolation. So any question? I think I should stop the recording and